Clock in the room. It's been 10 o'clock for the last hour. We got it? Okay. But it is time for us to start. So we learned about aldehydes and ketones, nomenclature, interesting compounds on Friday. Today we're going to talk about how we prepare aldehydes and ketones, reviewing reactions we've already learned for those purposes. Then we're going to go in more depth into some of the nucleophilic additions. We've already studied some nucleophilic additions of aldehydes and ketones. We're going to do two new ones, cyanohydrin formation and the Wittig reaction. So I've drawn for you on the board methods we've already learned for preparing aldehydes. We can perform PCC oxidations with primary alcohols. And that will give us an aldehyde. And remember, we learned last semester why this oxidation stops at the aldehyde and why it does not go forward to oxidize the aldehyde to the carboxylic acid. That's something you should remember or review if you don't remember. And then we can take esters or acid chlorides. I've drawn it on the board here with an ester. But esters or acid chlorides are interchangeable in this reaction. They can be reduced with Dibol. Or they can be reduced with lithium tritert butoxyaluminum hydride, either of those reducing agents. The key is to run the reaction at minus 78 degrees, and we explained why that's important in our last chapter. And then we add water and we generate an aldehyde. So the first one's an oxidation, the second one's a reduction. And then over here, our third method that we've learned, we learned in chapter 11 last semester. We can perform a hydroboration oxidation of an alkyne. That generates the less substituted enol. And we learned that enols, when formed, will tautomerize to give carbonyl compounds, in this case, giving an aldehyde. Okay? So those are the three methods we've learned for synthesizing aldehydes from three different types of starting materials. Any questions about those reactions? Okay, so with that, I gave you these reactions to kind of jog your memory a little bit. So now I'm going to ask you, what reactions have we learned to prepare ketones? There are some that are analogous to the reactions used to prepare aldehydes, and then there are some that only work for ketones. So let's see if we can remember. We can raise our hands and remember ways that we've learned of preparing ketones. Okay. All right, Trent? Yes. So we can perform a Friedel-Crafts acylation. So we're going to have a benzene or a substituted benzene as our starting material. Okay. And then what do we react that benzene with? An acid chloride. Okay. And then we need aluminum trichloride as our Lewis acid. And that's going to form a ketone. I'm just going to draw a line to the center of the benzene ring with R here. That's just a shorthand form of indicating that we would get mixtures of isomers. We would get ortho and para products because we know we couldn't do this reaction if R was a meta-director. Okay? But that allows us to prepare ketones where one of the groups is an aromatic ring. Okay? And we're using an acid chloride reacting with a benzene ring. Is there another reagent that we just learned about that can react with acid chlorides to make ketones? Yes? Organocuprates, very good. Okay. So we can take an acid chloride, we can react it with an organocuprate, and we add water. Remember, this water's not protonating anything to make a product. It's just quenching the byproduct of the cuprate. But after these two steps, we end up with a ketone. So acid chlorides and organocuprates, acid chlorides and aromatics, two different ways of making ketones. Very good. I'll give you a hint. There are two more methods that are analogous to two of the methods we have on the board for forming aldehydes. But they do require you to think back to last semester. Yes? Okay, chromium reagents, chromium oxidations. So what kind of alcohol would we start with? If we wanted to make a ketone, secondary, right? Primary alcohols in PCC will give aldehydes. Secondary alcohols and any of our chromium reagents will give ketones. So it doesn't matter which one we choose. Let's just choose chromium trioxide. We need water and sulfuric acid in this case. And that's going to generate a ketone. Okay, good. Okay, one more that came from last semester. That is comparable to this one right here. Complementary, I should say, to that reaction. Anybody remember how to make ketones from alkynes? Maybe I'll have to put that on our next synthesis problem on a test then. Hydration of alkynes, okay. So if we take a terminal alkyne, we're going to react it with water, and then what else do we need to put in the reaction mixture? Okay, we need sulfuric acid. And these are the conditions for hydrating alkenes as well. When we're hydrating an alkyne, we need to add mercury sulfate as well. That enables us to bypass the high energy vinyl carbocation intermediate. But this follows Markovnikov's rule and forms the more substituted enol, which then tautomerizes to generate a ketone with a methyl group in this case, okay? So if you don't remember that, I would suggest just briefly reviewing that in chapter 11, okay? And this is not number 3, this is number 4, sorry. So 4 methods of making ketones. There's actually a 5th. There's a method that works for generating ketones and aldehydes that's not on the board right now. And that starts from alkenes. So as I write an alkene on the board, maybe someone can raise their hand and let us know what reaction will form ketones and or aldehydes from alkenes. Yes? Ozone, yes, the ozonolysis reaction will allow us to form ketones or aldehydes depending on the nature of our R groups on our alkene. So we use ozone in our first step, and then there's a couple of different ways. We can use dimethyl sulfide, we can use zinc or water, but this process cleaves both the pi and the sigma bond of our alkene and would generate 2 products, which depending on the nature of our R groups could be 2 aldehydes, 2 ketones, or an aldehyde and a ketone. Usually this reaction is only practical when you want one of the 2 products because you usually would end up with, depending on your substituents on your alkene, a higher molecular weight species and a lower molecular weight species that you would separate by distillation. So usually you would just boil off the smaller one and you would save the larger one. So typically only one of the 2 carbonyl compounds is what you're looking for in this reaction. But they could be either an aldehyde or a ketone depending on the nature of these groups. So ozonolysis works for making either one, okay? So we have lots of different ways of synthesizing aldehydes and ketones, and we have lots of different starting materials we can use. We can use alcohols, acid chlorides, esters, alkynes, alkenes. So the good news is we can obtain aldehydes and ketones from a variety of different starting materials. So once we obtain them, what do they do? Well, we learned in chapter 20 that they undergo nucleophilic additions. Right? This was how we drew aldehydes and ketones in one structure. We have either some sort of an R group or a hydrogen here. And we learned that we can react strong nucleophiles. Usually they have a partial negative charge, but we're showing them in this fashion to indicate that they're strong nucleophiles. And then we add water. And so we're adding our nucleophile and a proton across our carbonyl. So we're making alcohol products from these reactions. Okay. We're going to learn more types of these nucleophilic additions in this chapter, including ones that involve some neutral nucleophiles, weaker nucleophiles than the ones we saw, and different types of nucleophiles from the ones that we saw in our last chapter. And we'll learn a new mechanism of this nucleophilic addition process. There's another reaction that aldehydes and ketones can undergo if they have at least one hydrogen on an alpha carbon. Okay? So I'll draw this species. This would be a ketone with a methyl group here. I've only drawn out one of the hydrogens. If you treat that with a strong base, that strong base can deprotonate one of our alpha hydrogens. And this should look pretty unusual. We're not used to seeing carbanions with a negative charge on carbon. Those are pretty rare intermediates. But in this case, we are generating a resonance stabilized carbanion because this is an allylic anion system. So we can draw a second resonance structure that's going to look like this. Which of these two species is the major contributor? Left or the right? Right, okay. We have the negative charge on the more electronegative atom. So what we have is a negative charge on the oxygen that's close to 1 and a negative charge on the carbon that's closer to 0. But because we have resonance stabilization, then we are able to deprotonate this species with strong bases. This is chemistry we're going to learn about in chapters 23 and 24. This intermediate has a name. It's known as an enolate. And it's going to react with electrophiles. It's going to be nucleophilic. It's going to react with electrophiles. You could have that electrophile react at the oxygen or the carbon of this intermediate. It's going to prefer to react on the carbon because that gives a product that retains that strong carbon-oxygen double bond. Okay, so two characteristic reactions of aldehydes or ketones, nucleophilic additions, and then enolate chemistry. Enolate chemistry is going to be the subject of chapters 23 and 24. In this chapter, we're going to focus on nucleophilic additions, which we've already looked at somewhat in chapter 20. So we have general mechanism of nucleophilic addition. And we saw this in our last chapter where our nucleophiles were either Grignard reagents or organolithiums or metal hydride species, borohydride or aluminum hydride. And then we protonate with oxygen in a second step. These are all strong nucleophiles. We can also react carbonyl compounds with weaker nucleophiles, but those weaker nucleophiles are not nucleophilic enough to attack a neutral electrophile, such as a carbonyl. And so we have to protonate our carbonyl group first to make it more electrophilic. Okay? So in these reactions, we need an acid This is acid catalyzed. We protonate the oxygen with a strong acid. That generates a resonance stabilized conjugate acid. Which of these resonance structures is the major contributor? The left or the right? Okay, left, why? Okay, yeah, over here on the right, this carbon does not have the octet. All the atoms in the resonance structure on the left have the octet. So the positive charge is primarily on the oxygen. And then in our second step, now that we've protonated the carbonyl, made a more potent electrophile, now weaker nucleophiles are able to attack. The book has drawn this using the minor contributor of these two resonance structures. And you can use either one. Whenever we have a resonance stabilized intermediate, you can draw the mechanism with either of those resonance structures, and it works, it's valid. But personally, I like to use the major contributor because when you use the major contributor, then you have a better picture of what the actual structure of the intermediate is. When you draw it with the major contributor, the structure you're drawing is more reflective of the actual structure of that intermediate. So if we were going to draw this second step of the mechanism using the major contributor, it would look like this. We would just have to draw two curved arrows instead of one. And we would end up with the same intermediate that the book does, which would then be deprotonated in step 3 in the same fashion by the conjugate base of our acid that we used. Okay? Are there any questions on this second mechanism, second general mechanism of nucleophilic addition? Yes? Usually it has to be a strong acid, so an HX type of acid or a sulfuric acid. Those are the acids. Toluene sulfonic acid is one we'll see in this chapter used for that purpose, but in the vast majority of cases it needs to be a strong acid. Okay, so let's look at some of the nucleophilic addition reactions we're going to learn in this chapter. And you see the two that we've already learned, reduction of a ketone, addition of a Grignard reagent or an organolithium. And then you see 5 that we haven't learned. And you see only one of these 5 retains the alcohol in the product. So most of the addition reactions, nucleophilic addition reactions we're going to learn in this chapter are going to have subsequent chemistry going on after the nucleophilic addition. In these 3 reactions, you have elimination steps that are going to occur. This is called the Wittig reaction. We're eliminating out this interesting looking molecule called triphenylphosphine oxide. Then when we make imines and enamines, we're eliminating water from this intermediate here. And then down here, we're going to have a substitution where we're going to replace this alcohol, this OH with an alcohol, making another ether. Okay, so many of the nucleophilic addition reactions we're learning in this chapter are going to be a little more complicated than the ones we learned in the last chapter because there will be other chemistry occurring after the nucleophilic addition. So that oxygen that originated from the carbonyl oxygen is not present in many of these products. Okay, so we see a variety of nucleophiles here. Ones we'd recognize as strong nucleophiles with negative charges. Down here we have alcohols. Those are weak nucleophiles. But there's one strong nucleophile that we're not seeing. So we don't see chloride or any halide for that matter. Our halide ions, we know those are strong nucleophiles. We learned that in chapter 7. Why are we not able to attack an aldehyde or a ketone with a halide ending up with an intermediate such as this. Well, why does this not work? Any ideas? Yes, Brady? Okay. So we know that when we have intermediates like this with a good leaving group, then we simply eliminate that leaving group. And so we would just go back where we came from. And if we adjust the arrows here for this process, we would see that this reverse reaction is much more favorable than the forward reaction would be. Another way to look at this is we have a chloride ion as one of our reactants, and we have an alkoxide as the product. Which is more basic, chloride or alkoxide? Alkoxide is a much stronger base, so the equilibrium would definitely favor the weaker base. So halides will not work as nucleophiles because of this acid-base chemistry, the fact that it would require converting a weaker base into a stronger base. So we won't see halide nucleophiles, but we see a lot of other types of nucleophiles. Okay. So let's briefly review a nucleophile we've seen before, a Grignard reagent. This sample problem from the book partially addresses an important issue of adding nucleophiles to aldehydes or ketones, and that is stereochemistry. In this case, we're starting with a chiral ketone, and we're generating a second stereocenter. And whenever we do that, whenever we generate a new stereocenter on a molecule that has an existing stereocenter, we have the possibility of forming diastereomers. So the book has nicely identified that. You see that we get diastereomers of these tertiary alcohols that are formed. What the book didn't mention is the issue of the ratio of these products. So that gives me the opportunity to ask you, are we going to get a one-to-one mixture of these products, or will there be a major isomer? Okay, I heard one-to-one. Brady? Brady thinks major. Okay, good. Why do you say there's going to be a major? Okay, so the methyl group is going to shield the top face of the ketone. And so that steric hindrance is going to cause the Grignard reagent to attack the back face of the ketone faster than it attacks the top face. So that means that this would be our major product with that ketone coming in from the back face, and this would be the minor product. Okay, so usually when we have a chiral ketone in these sorts of reactions, one face is going to be more hindered than the other. It's a little harder to see. It would have been nice if they would have drawn the Grignard reagent over here, because we know the Grignard reagent is not going to approach this ketone from the same side as that electron-rich oxygen. You're not going to have two electron-rich species approaching from the same side. What you will have, and it's the chloride, okay? Whenever you add a nucleophile to a carbonyl, you have to approach directly opposite of the oxygen. So you're approaching on this trajectory, and you have to approach either above or below the plane. You can't approach in the plane. And so if you're approaching in this fashion, you can see that that nucleophile is going to want to come in opposite the methyl group because of the steric hindrance that you would have if it approached from the same side. So we're going to have this as our major intermediate that is formed, and then we protonate that oxygen to generate the major product. Okay, so when we can predict a major product, we need to be able to do so in these reactions. Okay, Any questions? All right, let's move on to a new nucleophilic addition reaction, one we haven't learned yet. That's the addition of cyanide to an aldehyde or a ketone. And that's going to generate a type of compound referred to as a cyanohydrin. We're going to use sodium cyanide as our source of cyanide ion. And then we're also going to use HCl in this reaction. And so this product here is known as a cyanohydrin. It has an OH group and a cyanide group attached to the same carbon. So that's where the name cyanohydrin originates from. Okay? This is an important reaction because it forms a carbon-carbon bond. It allows us to extend the chain by one carbon. Extending the chain of our aldehyde or our ketone by one carbon by forming this carbon-carbon bond right here. And then the other thing that makes this reaction important is this nitrile functional group can be converted into a carboxylic acid, which is another useful functional group. So it's a way of converting ketones and aldehydes into carboxylic acids with one more carbon in the chain. So let's look at the mechanism of this reaction. And our cyanide is a negatively charged species. So it is a strong nucleophile. Okay, this is what our Lewis structure of cyanide looks like. So cyanide can attack our carbonyl carbon directly, giving us a tetrahedral intermediate. Can be formed from either an aldehyde or a ketone. And then we have acid in the reaction mixture. We added HCl, but you'll notice that I'm drawing HCN and using that as the acid to protonate our oxygen. Okay, as I'm drawing this, think about why I used HCN instead of HCl. And then when you know the answer, raise your hand and tell the class, why did we use HCN as the acid in this step and not HCl? Yes, please. Okay, so we're going to form HCN in this step, or form cyanide in this step, and then we can use that again. That is a feature of this. Yes? Yes, so HCl is a stronger acid than HCN. Put another way, cyanide is a stronger base than chloride is. Cyanide is a weak base, but it is a stronger base than chloride. Chloride's really not a base at all. And so when you have cyanide ion in the presence of HCl, your HCl is going to protonate the cyanide because you're converting a strong acid into a weak acid. Right? We've learned that that's thermodynamically favorable. So when you mix a cyanide source, such as sodium cyanide, with HCl, you're going to get HCN. And so you're not going to have the HCl, you're going to have the HCN here. Okay? Why don't we just add HCN to begin with? Why do we add these two reagents instead of just adding HCN by itself? Any ideas? There's a couple reasons. One is a practical reason. HCN is a toxic gas. Gases are difficult to work with, and we try to avoid things that are toxic. Okay. Sodium cyanide is also toxic, but it's not a gas, so it's easier to avoid inhaling it since it's a solid. Okay. So that's one reason, but there's another reason. If we used HCN, because it is a weak acid, it's not going to dissociate very much. So we're just going to have a teeny tiny amount of cyanide, not enough to accomplish step one. Okay? You might ask, well, can HCN protonate the carbonyl oxygen? Can we do that other mechanism where we protonate first? The answer is no, because HCN is too weak of an acid. It's not going to protonate the oxygen of the carbonyl very strongly. So we would need a strong acid to do that. But when we do this reaction, the book did not explicitly mention it, but we want to use excess of our sodium cyanide so that we don't protonate all of it, right? So it doesn't have to be a full equivalent excess. Let's just say we're using about 1.2 equivalents of sodium cyanide to 1 equivalent of HCl. If we do that, we're going to get 1 equivalent of HCN and 0.2 equivalents of cyanide. So we'd have enough cyanide in there to start the reaction. And then as we start to protonate this intermediate, we generate more cyanide. Let me just go ahead and write that over here so we can see that we generate more cyanide in that second step that could then be used. So because of acid-base chemistry, we want to add these as 2 reagents instead of just 1, and we want to use a slight excess of our sodium cyanide relative to our HCl. Any questions about that process? Yes, Trevor.
You said earlier that you asked why we would use HCN instead of HCl for the last step. Can you repeat that?
The reason why we don't use HCN? Because it's a weak acid, so it's not going to dissociate very much. You'd have too little cyanide for this first step to occur. And also because it's a weak acid, you couldn't do the other mechanism where you protonate the oxygen first, because it's too weak of an acid to do that. Okay, so for those 2 reasons, we need to use these 2 reagents. That also allows us to avoid a toxic gas, so that's a good thing as well. Okay, so the utility of our cyanide compounds, there's a couple of different things we can do with them. So we can treat a cyanohydrin with a strong base. Hydroxide is the most common strong base that is used. And we can eliminate cyanide from a cyanohydrin. This is usually not what we do with cyanohydrins, because this just gets you back to the aldehyde or ketone that you use to make the cyanohydrin. So this is less common, but it's important to know about this reaction, because if you have a cyanohydrin and you don't want this to happen, you have to avoid using base. Okay, so you typically aren't going to react your cyanohydrins with base. Okay, unless you do it in the presence of heat, because that's going to allow you to do a reaction involving water, where we're going to use either acid or base. And if we have heat present, that's going to allow us to hydrolyze our nitrile, where we're going to convert all 3 of the carbon-nitrogen bonds in our nitrile into carbon-oxygen bonds. And what that gives us is a carboxylic acid. Okay? So this is a more common procedure that is performed with cyanohydrins, converting them into carboxylic acids. Okay? Later on in the class, when we learn about amino acids, we'll learn about a process related to cyanohydrin formation that allows us to make amino acids. That's a very useful reaction. Okay, so this is most commonly what we do, and we're going to learn the mechanism of this hydrolysis later on. We're going to learn that towards the end of our next chapter. We're not going to learn that mechanism right now. Okay, so cyanide, as you're probably aware, is toxic. When you have cyanide in your body, it's going to bind to iron cations. Your body requires iron to be able to store and transport oxygen in proteins such as hemoglobin and myoglobin. But cyanide binds to iron much more strongly than those proteins do. So if you ingest cyanide, you just sequester all of your iron, and shut down your body's ability to store and transport oxygen. There are some naturally occurring compounds that contain cyanide. These molecules, they look kind of like cyanohydrins. They're not exactly, because they're ethers instead of alcohols, but they're relatives of cyanohydrins. Cassava root is eaten in Africa, but it is not eaten raw. It is boiled or roasted, and that cooking process destroys this molecule and destroys the cyanide in that molecule. So the cyanide is removed before it's eaten. Amygdalin is present in things like peach pits, apricots, cherries. So if your mom ever told you that there was something toxic inside of a peach pit or an apricot pit, that's what she was referring to. Okay, so don't eat those. Of course, you'd probably break your teeth before you were able to ingest enough cyanide that could do some damage to you. But there are many reasons not to eat peach pits or apricot pits then. Okay, and this is what happens in the body. Enzymes would cleave this cyanohydrin derivative to generate a cyanohydrin, and then another enzyme would eliminate out the cyanide and give you this toxic byproduct. All right, so with what we've learned about cyanohydrins and the chemistry of nitriles, we should be able to use nitriles in a multi-step synthesis. So let's get our iClickers out. Many of these reactions are reactions from previous chapters. Let's figure out what the identity of this final product is. And I'll tell you one thing, LAH, I'm not sure if we use that abbreviation in the book or not. That's simply an abbreviation that means lithium aluminum hydride. So we know what lithium aluminum hydride does. That's what's used right here. And then PCC, we know what that does as well. So we should be able to figure out the identity of compound 3. Go ahead and talk to your neighbors and answer the question. All right, let's start getting some answers in. It looks like they're coming in now. Let's finish this off in the next 20 seconds or so. Looks like we've got a debate between two answers going here. Let's see which one wins. Okay, let's keep those answers coming. Let's get those in the next 5 or 10 seconds here. Okay, any more? Any more than 26? All right, that looks like what we have today. Okay, we'll go ahead and close that off. All right, let's go through this step by step. What do we get when we treat a nitrile with aqueous acid and heat? We get a carboxylic acid. Very good. What do we get when we expose a carboxylic acid to lithium aluminum hydride followed by water? We get an alcohol. What kind of alcohol? Primary alcohol. So the answer then comes down to, what is the product when we oxidize a primary alcohol with PCC? Aldehyde, right? We had it right here on the board for you. So if you made it to this step, the answer was here on the board. Remember, we stop at the aldehyde because there's no water present. We cannot generate the hydrate intermediate that is necessary to oxidize to the carboxylic acid. So B was our correct answer. Okay. Let's talk now about a unique nucleophilic addition reaction to aldehydes or ketones. This one loses the oxygen from the carbonyl. This is known as the Wittig reaction. This is named after Georg Wittig, a German chemist. The Wittig reaction is a very, very important reaction, and that's reflected in the fact that Professor Wittig won the Nobel Prize in 1979 for discovering this reaction. So the reagent that is used, a Wittig reagent, it's a very unique looking species, and I forgot there's a positive charge on this phosphorus atom. It's got a carbanion species, a negative charge on this carbon. And you'll see that we make alkenes in Wittig reactions, but it's different from the way we made alkenes last semester because we are forming a carbon-carbon bond. We're forming a carbon-carbon sigma bond and a carbon-carbon pi bond. So we're actually able to make an alkene and lengthen the chain of our molecule at the same time. Our previous reactions for making alkenes involved eliminations where we already had to have the carbon backbone in place in the molecule. So this is a very useful process because it allows us to lengthen the chain and make an alkene simultaneously. And then we have this byproduct. This is known as triphenylphosphine oxide. We'll explain why that's important in a moment. But to understand the Wittig reaction, the first thing we need to do is understand the Wittig reagent. So a Wittig reagent is part of an interesting class of compounds known as ylids. Okay? This funny looking word is pronounced ylid. An ylid is a species where we have oppositely charged atoms bonded to each other. So it's a subset of zwitterions. In chapter 19, we learned about zwitterions when we were learning about amino acids. Zwitterions are molecules that have positively charged and negatively charged atoms present anywhere within the molecule. If those atoms are bonded to each other, then it is an ylid. So this is a subset of zwitterions. Phosphorus is a third row element. And because it is a third row element, it can exceed the octet. It has d orbitals that allows it to exceed the octet. So with a phosphorus ylid, we have a second resonance structure that we can draw with a carbon-phosphorus double bond. Okay? We have 5 bonds to phosphorus. That works fine because it has those d orbitals. The phosphorus is now actually neutral because it owns 5 electrons. It's in the 5th column of the periodic table. It wants to own 5 electrons. Now it does. Over here it only owned 4. So which of these two species is going to be the major contributor, left or right? The right's going to be the major contributor. So in the ylid, there is a negative charge on the carbon, but that negative charge is closer to 0 than it is to 1. However, the magnitude of that negative charge is high enough that an ylid can function as a strong nucleophile. Okay? So our ylids are going to be strong nucleophiles, but the charge on that carbon is going to be closer to 0 than it is to 1. So how do we prepare Wittig reagents or ylids? There's a two-step process that is used. We start with triphenylphosphine, and the phenyl groups, those are just functioning as spectators in this reaction. Okay? If we had alkyl groups on the phosphorus, for reasons we won't get into, those molecules are not very stable. And so the triphenylphosphine is stable enough that it allows us to generate these Wittig reagents. So phosphorus is in the same column as nitrogen, and we've seen nitrogen compounds, we've seen amines sometimes function as strong nucleophiles. So in the same fashion, we can use a phosphine in this case as a strong nucleophile in an SN2 reaction, and that generates a phosphonium salt, where we now have 4 bonds to the phosphorus. And then we're going to have a halide counter ion to that the phosphonium. Okay. So that's the first step in preparing a Wittig reagent. By virtue of being bonded to a positively charged atom, the hydrogens on this carbon are more acidic than a normal hydrogen attached to a carbon would be. And so this allows us to use a strong base. Organolithiums are commonly used, such as butyllithium. I need one more carbon for this to be butyllithium. We learned in chapter 20 that organometallics, organolithiums, and Grignard reagents can be used as bases. They're very strong bases. So in this case, our butyllithium would deprotonate. We're forming butane as a byproduct, and we're forming our ylid. And then our anion in this case is just forming a salt with the lithium that we had here. Okay, so 2 steps from alkyl halides. Only primary or secondary alkyl halides. Why not tertiary? What would happen if we tried to use a tertiary alkyl halide in this first step? Okay, there's no hydrogen, so we wouldn't be able to deprotonate it in step 2. We wouldn't even make it to step 2, because what kind of reaction is this? SN2? That sound familiar? What do we remember about SN2 reactions and tertiary alkyl halides? It doesn't work. Tertiary alkyl halides are too hindered. So not only would we not have a hydrogen to deprotonate to make our ylid, we couldn't even make it to this point if it was a tertiary alkyl halide. So this only works with primary or secondary or methyl. We can use methyl halides in this reaction as well. Okay? So starting from alkyl halides is how we make, or methyl primary or secondary alkyl halides is how we make Wittig reagents. Okay? So once we make a Wittig reagent, how does it react? What's the mechanism by which a Wittig reagent will react with a ketone or an aldehyde? It's a 2-step mechanism. It's a little different from mechanisms we've seen before. And I'm going to go ahead and use our simplest ylid or simplest Wittig reagent. This would be made from a methyl halide, such as iodomethane or bromomethane. Okay. So I've drawn the minor contributor for you. I just told you earlier in class that usually I like to use major contributors, but with Wittig reactions, I think it's actually a little easier to see what's going on with the minor contributor. But you could draw the mechanism with the major contributor as well. But we've got this lone pair and this negative charge on the carbon. That's going to be nucleophilic. So it shouldn't be surprising to see that attack the carbonyl carbon. Every time we've attacked a carbonyl carbon previously, we've pushed electrons up onto the oxygen. But we're not going to do that this time. We're going to push the electrons onto the phosphorus. We're going to make a four-membered ring. Okay, so that's unusual. Four-membered rings are strained. Right? And so they're a little more difficult to make because of that strain. So why does this work? Why do we do this? Well, phosphorus-oxygen bonds are quite strong. And so that provides a thermodynamic driving force for this reaction. We've generated a strong phosphorus-oxygen bond that allows us to overcome the ring strain inherent in forming a four-membered ring. But we do have ring strain, and there's a way to alleviate that ring strain while at the same time forming a second strong phosphorus-oxygen bond. So we can break open our four-membered ring by cleaving sigma bonds and forming pi bonds. Usually we don't do that. Usually we go in the other direction, converting pi bonds to sigma bonds. But because we're releasing ring strain and we're forming a strong phosphorus-oxygen bond, then we're able to do that in this case. And we generate our alkene, and then we form this byproduct, this triphenylphosphine oxide, where we now have two strong phosphorus-oxygen bonds. So the formation of a strong phosphorus-oxygen bond in each step of the Wittig reaction provides a driving force, allowing us to form this strained four-membered ring, and then allowing us to convert sigma bonds into pi bonds. Okay, so two unusual things happening in this reaction, both of which are possible by generating phosphorus-oxygen bonds. Any questions? All right, we'll stop there. We'll learn a little more about the Wittig reaction and some of these other addition reactions to aldehydes and ketones on Wednesday.